100 compound. And then I told our DFT collaborator, let's calculate them. And this has been very successful. And one of the first successful cases is tungsten arsenide. We sort of published, post a paper concurrently with Professor Shida and Tongdong's group with IOP. So here you can sort of see a similar picture because, arsenide will be 3 minus. So then arsenide will form a full shell. But then tantalum 3D will basically lose all the D electrons. But then, it's not a full shell condition, but all the subshells are either empty or full. So this is one of the examples, and we have actually found many more. So in the rest of my talk, I'll tell you some of our other predictions, and then my colleague Nasser Alidust will talk about the RPES experiments. So, for example, this is a compound strontium silicide, and here you see a similar scenario as sodium 3 bismuth because silicon is sort of in a obscure or unusual valence state. Now it's you see that it's -1, but usually if you think about silicon dioxide, it's +4. So indeed, this is a semimetal, and one thing that is special is that the Weyl fermions are quadratic. So that means the tidal charge of the Weyl fermion is actually +2 or -2. And that is because two single charged Weyl fermions are actually bonded together at the same K point because of an extra crystalline symmetry. And this is because of the cubic symmetry here. And so this is one of the example. So also there's this TMDC, the moly or tungsten telluride in the TT phase. So here, we are a little bit behind Professor Bernwick's group, and they also point out that this is a type 2 Weyl fermion. But then they were doing WT2, and the problem with WT2 is that the separation of the Weyl nodes is extremely small. It's within the experimental resolution or whatsoever. But our idea is that if you dope moly, then the splitting of the Weyl fermion will be increased, and then you can experimentally observe it. But still, there's a problem that the Weyl nodes are above the Fermi level. So that means, number one, it's hard for photoemission, and number two, if you do transport, you're not going to see the chiral response because at the Fermi level, everything's gone. So, but this is good because many people are doing TMDC and it's layered, so maybe when you scotch tape, you could train the chemical potential, so there's a hole there. So then we were trying to look for other type 2 Weyl semimetals, and then we come up with this guy, tungsten sulfide. And here you see that the Weyl points are very close to the Fermi level. You also see from the schematic that the Weyl points are well separated. So this has, we're still doing experiment on this, but the theory is very clean. So this is unpublished, so I'm not allowed to tell you the chemical formula, but we have a ternary compound that is extremely clean. So you see that within ±1 eV, we have nothing but the Weyl points. And when you look at the Fermi arc, it's beautiful. It's like a Tai-Chi diagram or whatever in China. But so this is again a very exciting compound. And let's see. Finally, we have this another ternary compound, and where it turns out that we already see this type 2 Weyl crossing. You see that you have a band crossing between two bands that have the same sign of velocity. So I'm not going to talk about the RPES. My colleague will talk about it, but I just want to say that to do the RPES, you have to basically show these 3 critical components. So these are all topological arguments. It's not just compare theory with experiments. And then I want to highlight that our group and Professor Hongding's group, IOP, did the first RPES experiments on this class of materials. And now this is very exciting. Many other groups, including us, are doing more RPES and other experiments on these compounds. And I'm gonna acknowledge all the group members and also our collaborators and Beamline Scientist Founding Agency. And let me just conclude that we have searched through the chemistry database to identify the compounds that satisfy symmetry considerations for biosemimetal state, and then we have used our intuition to narrow down the number of candidates and then do systematic calculation. Through this process, we have found a number of biosemimetal candidates. This includes both I breaking and T breaking, and many of them are still not published. So in the following month, you'll see a number of archive papers. Thank you.
There have been several other proposals of Weyl semimetals in magnetic compound before TaAs compound. Have you ever tried to?
Yes, of course. Thank you. So the first biosemimetal candidates were all like iridate, mercury chromium selenide by Professor Shidai. All these are ferromagnetic. So we have tried all of them, especially the mercury chromium selenide has a very reasonable Curie temperature, and the crystal can be grown quite big. We just didn't get any good signal. I think one of the problem is that you can't. So in RPES, if you cool it down, you get the ferromagnetic phase, but then you still have many magnetic domains, right? And your RPES beam spot is usually like hundreds of micron, and the magnetic domain is like several micron. So basically, you average over 100 magnetic domains, and you can't apply magnetic field in RPES. That means you can't align the domains. So you have random domains, and your band structure critically depends on the domain, right? So that might be one of the problems, but we're still trying. I think in the future we might be able to find a T-breaking biosemimetal, but it's not there yet.
Okay. Actually, I have one quick question.
Yes.
For the double Weyl, the silicon tube, does the cubic symmetry kind of protect the Weyl from the surface, or there is no protection?
Yeah, so the cubic symmetry, not the cubic, actually, cubic means that you have 3 C4 along ABC. Both are all of them are C4. So the C4 symmetry protects the double Weyl. So if you break the C4, then the double Weyl will split into 2 single Weyls.
Yeah, but is the Weyl known as a Fermi energy, or it's quite?
You can see it's not exactly at the Fermi energy, but it's like 10 MeV or 20 MeV. It's fairly clean. So this is one of the other problems that many people are asking me, that can you find a biosemimetal with only 2 Weyl nodes, and then they're exactly at the Fermi level. And this is very hard, especially if you have some crystal symmetry, then you always copy it many times. So that would be hard. Yeah.
Nice. Thanks. Okay, so I think let's move on. Let's thank the speaker again.